All right, next up is resonance, right? And so similar to atom effects in terms of size, resonance, more resonance is better because a spread out negative charge is more stable, right? We want to spread this charge as far apart as possible. So for example, if we have something like this, right, OH versus this alcohol over here versus this carboxylic acid over here, and if we're to deprotonate both of them, right, on the left one, there's no resonance structures there. Whereas on this right one, right, we deprotonate it and then we can draw some resonance structures, right? We can kick the electrons from this oxygen into this double bond and then move these electrons up here. And so this one on the right, this negative charge is spread out over a larger area, or it has more resonance structures. And so it's going to be more stable, right? It's okay holding this negative charge relative to the alcohol. And so since it's more stable like this, it's going to be less likely to pick up an H+. So this will be the weaker conjugate base, which makes this carboxylic acid up here the stronger acid. Right, and then the alcohol, right, vice versa of that. Let's take a look at another case right here where things get a little bit more tricky. So we have this alcohol over here. We have this component over here, which is known as a phenol. And then we have our carboxylic acid, right? And we'll deprotonate each one of them, see how they're acting as acids, right? So we have this O- here, right? No resonance structures, not that great. Deprotonate this guy over here. And we can kick this negative charge all over the place, right? We can move it down here. And then we can further move it all around this ring. Right, and one more step. And then this next step right here, you'd go back to your original compound, right? So got a whole bunch of different resonance structures, essentially kind of 4 good resonance structures there. And then we have this carboxylic acid, right? If we deprotonate this guy, this O- here, and then we can draw kind of one more resonance structure here. Right. And so looking at these 3 structures, the first thing we notice is that this one's going to be the least stable. And so this will be the strongest base. And then this alcohol up here will be the weakest acid. And so then we can move on to deciding between these two, right? Which one of these two is more stable? And so remember our criteria. One is charge, right? They both have one negative charge, so that's not that big of a deal. Atom effects, at first we're thinking, well, the negative charge is on an oxygen in both of these things, so atom effects won't be that big of a deal. And then we're thinking resonance, right? And so this is where it gets a little bit tricky, right? Although this one has more resonant structures, you have to think about where this negative charge is. So you kind of want to go back to atom effects as well. While this one does have a negative charge spread out more, this one has a negative charge between 2 oxygens, right? 2 oxygens. Whereas this one spreads the negative charge around carbons, which as we've seen is not very stable. And so what ends up happening is that this carboxylic acid is actually more stable, or this conjugate base is more stable And so this guy right here is more acidic, or this is the strongest, or this is the weakest base, making the carboxylic acid the strongest acid. Right? And that's because this negative charge is spread over 2 oxygens, whereas in phenol, we'll spread over an oxygen and some carbons. So you kind of have to think about resonance structures and atom effects kind of together.